Redox reactions aren't just limited to ionic compounds. We know in ionic compounds, electrons are transferred from one element to another. In covalent compounds, remember, the electrons are shared between the elements. But for a redox reaction, we're not just talking about going from one element to another. We're talking about going from one compound to another. When the electron goes from one molecule to another molecule, it can still be an oxidation-reduction reaction. But for covalent compounds, it's a little trickier to figure out which thing is oxidized and which thing is reduced. To do that, we're using a concept called the oxidation number. The oxidation number is the charge that the element in the compound would have if the compound were ionic. We have a set of rules for determining the oxidation number. This set of rules is really important. You're basically just going to have to memorize this slide. Our first important rule is that the oxidation number of an atom in its elemental form, the way we find it in nature, is going to be 0. For example, the O2 molecule, or the F2 molecule, or S8, or zinc solid, or copper solid, would each have an oxidation number of 0. Our second rule is that if it's a monatomic ion made up of a single element, the oxidation number equals the charge on the ion. For example, the calcium 2+ ion has a +2 oxidation number, or the S2- ion has a -2 oxidation number. Our third important rule is that the total of all the oxidation numbers in a molecule or polyatomic ion equals the charge on that molecule or polyatomic ion. That means that if it's a neutral molecule with 0 overall charge, the sum of the oxidation numbers equals 0. If it's a polyatomic ion, the sum of the oxidation numbers equals the charge on that polyatomic ion. For example, sulfate has a -2 charge, so the oxidation numbers would add up to -2. Once we've thought about those three rules, we're also going to follow a list. The ordering of this list is important. The top of the list indicates that it's always going to happen. Fluorine will always have an oxidation number of -1. Lower on the list means it's likely to be the oxidation number, but it depends on the things that are earlier in the list. We follow our list from top to bottom when assigning our oxidation numbers. First of all, fluorine is always going to have a -1 for its oxidation number. Remember, fluorine is the most electronegative atom, so it's always going to get the -1. Group 1A metals always have a +1 oxidation number. Group 2A metals always have a +2 oxidation number. Hydrogen is usually a +1, but if it's bonded with something higher in the list, the thing that's higher in the list takes priority. For example, if hydrogen is bonded to fluorine, we would assign fluorine's oxidation number first, and then hydrogen would get the leftovers. Remember, the total of the oxidation numbers has to equal the charge on the molecule or the polyatomic ion. Oxygen is usually a -2, but if it's bonded with something higher in the list, the thing that is higher in the list has priority. Group 7A, other than fluorine, is typically going to be a -1. Fluorine is always -1, but the other 7A elements are just usually -1. Again, it depends on if it's bonding with something higher in the list or not. Anything not on this list is assigned last, and it will always get the leftovers of making the charge on the molecule or a polyatomic ion come out to what it's supposed to be. Let's go through a bunch of examples of finding oxidation number. We're going to find it for every atom within the compound. Let's start with potassium permanganate. We're going to list the oxidation numbers that we know, starting with the top of our list and working our way downwards. At the very top of our list is fluorine, which is not in this compound, but after that are the 1As and 2As. You have to be careful and watch out for them because they're not explicitly listed. You'll have to look at the periodic table if you don't have them memorized. In this compound, we have potassium, which is in group 1A, so it's going to have a +1 for its oxidation number. There's only one potassium, so its total contribution to charge is a +1. Next, we have oxygen a little further down on our list. and its oxidation number is typically going to be a -2. We go ahead and give it its typical -2 oxidation number, since we still have one more element to assign oxidation numbers to that can help us add up to a total of 0 overall charge. There are 4 oxygens. 4 oxygens times the -2 oxidation number gives us a total of -8 contribution to charge from the oxygens. Our total contribution to charge has to add up to the charge on the molecule or polyatomic ion. In this case, it has to equal 0. Essentially, we have +1 plus x minus 8 equals 0. X, the total contribution to charge for manganese, must be a +7. There's only one manganese, so it gets that full +7 oxidation number. Let's look at another example, sulfuric acid. The highest thing on our list right now is hydrogen, so it gets its +1 oxidation number. There are 2 hydrogens. 2 times +1 means the total charge coming from the hydrogens is a +2. The next thing on our list is oxygen. Oxygen has a typical oxidation number of -2. There are 4 of them, so 4 times -2 gives us a total of -8 coming from the oxygens. Again, this is a neutral compound, so our total contribution to charge has to equal to 0. +2 plus x minus 8 equals 0, so x must be +6. There's only one sulfur, so it gets that full +6 oxidation number. Let's look at an example of a polyatomic ion, the chlorate ion. We have 2 things on our list. Oxygen is higher on the list than the chlorine, so it gets its typical -2 oxidation number. There are 3 of them, so 3 times -2 gives us a total of -6 coming from the oxygens. Now here's the tricky part, because it's not a neutral compound. It's a polyatomic ion with a charge. We're trying to add up to that charge of -1. We have x minus 6 equals -1, so x must be +5. Since there's only one chlorine, it gets that full +5 as its oxidation number. We would say in this compound, chlorine has an oxidation number of +5, and oxygen has an oxidation number of -2. Notice that the chlorine does not have its typical -1 oxidation number. That is because the oxygen took priority. It is higher in the list. Let's look at another example, SO2. Oxygen is on the list, but sulfur is not. So oxygen gets its typical -2. There are 2 of them, which makes a total of -4 coming from the oxygen. This is a neutral compound, so we're adding up to 0, which means there must be a +4 contribution to charge from the sulfurs. And there's only one sulfur, so it gets that full +4 as its oxidation number. Let's look at sodium hydride. Again, we've got 2 things on our list. Sodium's in group 1A, and we have hydrogen. Since sodium is in group 1A, it has higher priority, so it gets a +1. There's only one of them, so it has a total contribution to charge of +1. We're trying to add up to 0. This is a neutral compound, so the other side must have a total contribution to charge of -1. Therefore, hydrogen ends up with a -1 for its oxidation number. That's not the typical oxidation number for hydrogen. Typically, hydrogen would be a +1, but because it's bonding with something higher in the list, it ended up being a -1 in this compound. Let's find the oxidation numbers in another ion, the carbonate ion. Oxygen is in our list, carbon is not, so oxygen gets priority. It's got a -2 for its typical oxidation number, and there are 3 of them, so 3 times -2 gives us -6. Again, because it's an ion, we're adding up to the charge of the ion, which is a -2. We have x minus 6 equals -2, so x must be +4. There's only one carbon, so it gets that full +4 for its oxidation number. Let's look at another example, N2O5. Oxygen is on the list, but nitrogen is not. So oxygen is going to get its typical -2. There are 5 of them, so 5 times -2 gives us a total of -10 on the right side. We know this is a neutral compound, so we're trying to add up to 0, which means our left side total must be a +10. But notice there are 2 nitrogens contributing to that +10 charge. Each nitrogen is going to end up having a +5 oxidation number. If we do our +10 divided by our subscript of 2, that gives us a +5 for the oxidation number on each nitrogen. What is the oxidation state for sulfur in HSO3 -1? Is it A -2, B +1, C +2, or D +4? The correct answer is D, +4. Oxygen is a -2, and there are 3 of them, so that's -6. We've got a +1 from the hydrogen. So +1 plus X minus 6 equals -1. So X ends up being a +4. Since there is only one sulfur, it gets the full +4 for its oxidation number.